Okay, let's talk about stoichiometry. Often I'll refer to it as stoich. It's a really important skill to have, especially if you go further into the sciences. You'll see it's used a lot in chemistry, it's used in medical field, it's used in engineering, all different kinds of stuff. So super important skills to have. So if we define stoichiometry, it's derived from the Greek word stoichion, meaning element, and metric, meaning measure. So if we look up the definition, it's kind of funny. It's just solving mass-mass relationships in chemical reactions. It's really a specific factor label process, but we could also use it beyond the mass-mass relationship. We could find liters or atoms or molecules or moles, all different things based off of this process. So just a reminder, we know that 1 mole is equal to the molar mass or the molecular weight off the periodic table. We know a mole is equal to 22.4 liters of gas. We know a mole is equal to Avogadro's number of molecules for a compound. We know a mole is equal to Avogadro's number of atoms. We could find the number of atoms per molecule by counting. I forgot to list that here. But all of those conversions are used in stoichiometry. So the most important thing that's new here is this mole-to-mole ratio. So really the only thing that is totally new is this mole-to-mole ratio. And what it is a ratio of the coefficients used to balance a chemical reaction. So it's just the number that's in front. So I could compare sodium and Fe2O3. So 6 to 1 would be the mole-to-mole ratio. Or I can compare Na to Na2O. So that would be 6 to 3. I can compare Na to iron. That'd be 6 to 2. I could do 1 mole Fe2O3 to 3 moles Na2O. 1 mole of this to 2 moles Fe. And then we could do 3 moles of Na2O to 2 moles of Fe. And that's probably every combination possible. Now don't worry about reducing these if they can be reduced. You might as well just keep it as is, and it reflects what's in that chemical reaction. So again, the mole-to-mole ratio is the most important part. So what we have here is the new mole roadmap. Okay, so if you look on this top part, this is the mole roadmap I gave you first semester. And the bottom part is the mole roadmap in just a different color. And so what is different now is this middle part is the mole-to-mole ratio. So this mole-to-mole ratio from the chemical reaction is going to connect 2 mole roadmaps together. So I can go from compound A to compound B, or I can go from a reactant to a different reactant, or a product to a product, or a reactant to a product, all based off of this mole roadmap. So theoretically, I could go from grams of A to moles of A to moles of B to molecules of B to atoms of B. I can do any variation here. Or maybe I just go moles of A to moles of B using my mole-to-mole ratio. So you need to be able to read this mole roadmap really well, and I would have this in a very, very handy place. So when solving basic stoich problems, make sure the reaction is balanced. If it's not balanced, none of this will work out. Write your givens above the compounds and question marks above the unknowns. Find where you are on the mole roadmap path. I think this is, I don't know, there's a typo there. Set up brackets to cancel units until you're left with what you're trying to find. And remember, top-bottom cancels, and multiply everything on the top and divide everything on the bottom. So what does this look like? So here's this first example problem. And it says we have 2 moles of potassium chlorate break up into 2 KCl and 3 oxygen gas. Here you're given 30 grams of this, and you want to know moles of KCl. So we're going to look at the mole roadmap, and we'll realize that there's 30 grams of KClO3, and we need to get to the mole roadmap to go from point A to point B, which means I must convert my mass in grams to moles. So this is where my molar mass, or my molecular weight from the periodic table, comes in. Okay, so that allows me to convert to moles. Once I know my moles of KClO3, I go to my balanced chemical reaction. So that's where that 2 came from. Okay, and the 2 moles of KCl go here. And my final answer is supposed to be in moles, so I actually wrote this wrong. So I shouldn't actually include this bracket, and you would find the number of moles is equal to 30 divided by 122.6 times 2 divided by 2, and you find it is 0.24 moles. Now, if I wanted this in grams, I would add on this additional step of then multiplying that by the molecular weight of KCl, and I'd find that to be the 18.3 grams. Okay, so it shows even when I wrote notes a while ago, I make mistakes. So just be really, really careful that you do answer the question that's asked, and hopefully you catch yourself if you do make a mistake. Now, if we look at the next question, we have 50 grams of KCl, and it wants to know total atoms of KClO3. So again, we're going to start with KCl. We know we have to go to moles because it's the only way we can convert from one compound to another. So I'm going to divide by the molar mass. So again, this is from the periodic table. And then this middle part is my mole to mole reaction, or mole to mole ratio from the balanced chemical reaction. So again, the 2 moles are from here. These moles are from here. And this is the only place that you'll have numbers that are different than 1. So then we're going to convert 1 mole KClO3 to molecules. And then we're going to take molecules to atoms. So this part here is like what we did first semester. So when we solve this out, it ends up being 2.0 times 10 to the 24th atoms of KClO3. Okay, so let's go ahead and try a couple practice problems here. So I notice this first reaction. I have the 2 KClO3 going to 2 KCl plus 3 O2. I'm starting with 5 liters. So 5 liters of O2. When in doubt, convert to moles, even if you don't know what you're doing. It's almost always worth points. I look at my mole roadmap, and I know that 1 mole is equal to 22.4 liters. So then I can go to my balanced chemical reaction. I have 3 moles of O2 to 2 moles KCl. Okay, and you always need to think about top-bottom canceling. Okay, so if I look at this, liters cancel, moles cancel, left with moles of KCl. So notice I wrote these out to double check. And when I solved this out, I found that to be 0.15 moles KCl. Okay. Now let's look at the next one. It's even shorter. So you're given 1.5 moles of compound E. And we're going to go to moles of compound A. So I don't need to convert anything first. I'm already in moles. So I can go direct to the mole to mole ratio. So 7 moles E to 6 moles A. Multiply the top, divide the bottom, and it's 1.29 moles of A. Okay, and we could also relate heat with stoichiometry. Now, heat is usually in kcals or calories or joules, and it's a special situation. So I have this reaction here, and it says how much heat is released when 20 grams of C8H18 is combusted. So we have to remember that we have these mole to mole ratios, and then I can make kind of this mole to heat ratio. This is what I call it, a mole to heat ratio. And we're actually going to come back to this again when we do a whole unit on thermochemistry, which is all about heat. So we're going to start with our 30 grams of C8H18. We're going to divide by that molar mass from the periodic table to get us into moles. And then we're going to find the number of moles from our chemical reaction, which is 2. And then we have that 1,000 kcals on top. Multiply everything on the top, 30 times 1 times 1,000, divided by 114, divided by 2, and you find this answer. So it's a very special situation, very specific. So I'm going to do a second video with a guided practice.